this video, I will be conducting a hypothesis test for a population mean using the p-value approach, assuming the population standard deviation is known. A random sample of 25 observations from a normal population has a mean of 22. Assuming the population standard deviation is known to be 4.9, can we conclude at alpha equals 0.01 that the population mean is significantly below 24? Since we're testing if the population mean is below 24, the alternative hypothesis will be that the population mean mu is less than 24. For the null hypothesis, we will simply assume that there has been no change in the population mean so that mu equals 24. Note that technically, the null and alternative hypotheses are supposed to be mutually exclusive. In essence, the null should be mu greater than or equal to 24 here. However, to simplify our explanation, we will simply keep mu equal to 24. Now, since we assume that the population standard deviation sigma is known, we will use the z-test statistic. In plugging in the values, we have a z-stat of negative 2.04. Now, this is a left-tail test, that is, a directional test with a less than sign in the alternative hypothesis. Therefore, the p-value will be the area under the curve to the left of the test statistic. From the less than z table, the area below z equals negative 2.04 is 0.0207, and that's the p-value. But what does it mean? It tells us that if the null hypothesis is true, the probability of obtaining a test statistic this extreme is only about 2%. In other words, if the population mean is truly 24, the chances of obtaining a sample mean of 22 or less from that population is only about 2 in 100 samples of the same size, the size being 25 in this case. The question then is whether the 2% chance is reasonable. Is it too small or is it too large? If the p-value is too small, it means that the sample mean is too far from the population mean, which is not supposed to be the case. Since a sample is randomly selected, its statistics should reflect the population parameter and not be too far from it. If nothing is wrong with a sample, then the problem must lie with the assumed population parameter. Hence, we reject the null hypothesis when the p-value is small. A large p-value, on the other hand, suggests that the sample statistic is close enough to the population parameter, and that will lead us into not rejecting the null hypothesis. Moreover, for our purposes here, we will be comparing the p-value to the specified significance level alpha. The significance level alpha, which we decide before conducting the test, is the smallest p-value at which we will reject the null hypothesis. That is, if the p-value is less than or equal to alpha, we will reject the null hypothesis. Otherwise, we will fail to reject it. Since our p-value is greater than alpha of 0.01, we will fail to reject the null hypothesis. Consequently, there is not enough evidence to conclude that the population mean is less than 24 at alpha equals 0.01. But if we're testing at alpha equals 0.05, our p-value will be less than alpha, in which case we will reject the null hypothesis in support of the alternative. That is, we have enough evidence to conclude that the population mean is less than 24 at alpha equals 0.05. Next, suppose we want to test if the population mean differs from 24 at alpha equals 0.05. Since differ or different could either be less or greater, this is referred to as a two-tailed test or a non-directional test. And the alternative hypothesis is written as mu not equal to 24. The p-value for the two-tailed test will be 2 times the one-tailed p-value because the one-tailed p-value is mirrored in the other tail of the distribution. And since the p-value is less than alpha, we will reject the null hypothesis and say we have enough evidence to conclude that the population mean differs from 24 at alpha equals 0.05. But if we test this at alpha equals 0.01, the p-value will be greater than alpha. We will fail to reject the null hypothesis and therefore cannot support the alternative. Next, let's look at a right-tailed test. We now have a sample mean of 26, a population standard deviation of 5.5, and we're testing at alpha equals 0.05 whether the population mean is greater than 24. This requires the alternative hypothesis to be mu greater than 24. The test steady state will be 1.82, and the p-value will be the area in the right tail of z equals 1.82. Looking that up in the z table or software, we find that the less than area is 0.9656. Subtracting that from 1, we have a right tail area of 0.0344, which is the p-value for this test. Since this p-value is less than our significance level alpha of 0.05, we will reject the null hypothesis. And we have enough evidence to conclude that the population mean is greater than 24 at the 5% significance level. Again, based on the same data, suppose we want to test if the true mean has changed from 24. This would be a two-tailed test because change could denote either an increase or a decrease. So the alternative hypothesis would be that the population mean is not equal to 24. We will multiply the one-tailed area by 2 to get the p-value, which in this case is greater than 0.05. That is, we fail to reject the null hypothesis this time, and cannot conclude that the population mean is different from 24 at alpha equals 0.05. And that's it for this video. Thanks for watching.